Welcome to another draft physics presentation and such. So just a general, still working on it kind of video, how to make the argument and try to do it as concisely and in the right order and procedure in terms of explaining how most of the concepts in physics are fundamentally wrong. Now, they might be right in a lot of ways, accidentally and because some of the systems are parallel, but that there's a basic design flaw, right at the foundation of the physics in terms of things like Einstein's bent space, his perception that time is a dimension that can be bent or warped, and most of the quantum mechanics in terms of its attitude, in terms of things like not recognizing that formulas are not wave equations, they're pattern equations, and that different things could be regulating what patterns are caused, and it doesn't have anything to do with any sort of Heisenberg kind of notion that elements of the universe don't have positions and don't have momentums, and just because we can't measure them. Again, these things don't arise as facts. There's so many things they establish as facts that are not provable as facts, because it's inaccessible. We can't prove it one way or the other. So they're basically assumptions, and I would argue that when they had a chance to make a right or wrong assumption, they've chosen badly. And it seems largely with a bias towards the more elaborate universe rather than a simpler universe. So the causes of why they made mistakes isn't really important. The important fact is that I think they can be demonstrated to be mistakes because they create problems and paradoxes that you just aren't going to be able to fix. Things like creating different kinds of force modalities where it seems kind of logically sensible. The evidence sort of suggests the idea that all the forces have the same speed and that they function under many of the same rules, that these forces are really a manifestation of one thing, not completely different things. That kind of stuff. So, in attempting to do this remake of physics, I thought it might be a good idea to try to establish a list of what we do know as facts. I mean, the secure stuff, the stuff that's solid, versus the stuff that is assumed to be true because it can't be proven not to be. The stuff that's more made up, for lack of a better word. And so I do have a list that I've started, and if you would like to, in the comments, to contribute some fact that you think needs to be placed on the list as an established fact, that would be welcome. I'll obviously, I think of more to add to this list as time passes. So the basic point is a more reasonable interpretation of the securely known and established facts. So the point is once you establish these facts, I think you can draw a picture of connecting their dots that they create that will be much more efficient and sensible than the one created by current physics, which is obsessed with very complex, obtuse mathematics even, and obsessed with models like the standard model of the electrons and the protons and then all these subatomic particles that they've seen for brief zillionths of a second kind of things. They never see them directly, they only see them indirectly, like the Higgs boson. They claim they found it, but they didn't find it really. They claim they saw where it banged into something, that kind of thing. Lots of statements in physics about things they know to be true that the evidence is really, really thin, weak, And so when you add up the real facts, it's really a very short list, I think. I think it's going to stay a pretty short list. of what we can securely say. And I think you can efficiently construct those facts into a diagram that's going to look a lot more like checkers rather than three-dimensional chess. And I think the right answer is the simpler answer that fits the facts. I think that's a reasonable theory. Alright, anyway, so we can say as a fact that there is an electron repulsive force and a proton repulsive force. There's obviously some kind of force that involves itself when electrons get close to electrons and they repel each other. Same with protons, and the inverse is true. The electron force is a friendly force to a proton, and the proton force could be considered a friendly force to I think I said that the other way around, but anyway. But the fact that there is some force involved, that they don't just hate each other by thought and then action. There's some mediating mechanism that is obviously transferred between them and transferred at the speed of light that communicates the idea that you will not stay in each other's company. There'll be pressure or reason for both of you, to find the current circumstance unacceptable and seek a new circumstance, that kind of thing. The inverse square law. Now, it's really just the inverse square tendency, but it's seen with all the forces. They all tend to radiate in every direction kind of way. And that's essentially what the inverse square law implies, is that everything starts from a point and it radiates out like a dandelion seeds or something in all directions. And the force rule, or law, breaks down when you put things really close to each other, because then the spread doesn't impact in a negative way, because all the spread of the stuff in this middle of my palm, let's say when the two palms are close together, all the spread still hits the other hand, and vice versa. So it's no longer inverse square because it's not escaping. But it tends to be the rule that force is admitted in this way, that energy is admitted in this way in a lot of circumstances. Obviously, we can change the rule by creating lenses and other mechanisms to confine where the light goes. And with some forces, we can direct them so they'll be more intense in one plane than they will in another plane. Even the filament on a light bulb is not perfectly inverse square. It's not obeying it as a law. It tends to be an even distribution of light, but it's not really an even distribution of light because the filament has a length to it in the case of a filament bulb. Alright, the speed of force. So we have this term, the speed of light, but it really should be the speed of force, to really understand that what we've established is that all of these things, these little bits, the little thing, the force between two electrons, and the force between two protons, and the force of gravity, and the force of light, which is essentially a force, all of these things move at the same speed. The magnetic changes in magnetism move at this speed, the speed of light. This effect that all these things radiate, that we call a force, all these forces of radiation have the same speed. So it's not really the speed of light, it's the speed of force, and it's better, in my opinion, it's better to understand that light moves the speed of force as a force. It doesn't move its own speed. It's just that it was the first thing we declared to have a speed, and by doing that it got misnamed. And a lot of that happened in the history of physics, where something was done sort of wrong and they never chose to fix it. Alright, a wave is energy change passing through connected tension. So the tension that is those little, whatever's being communicated between electrons and whatever's being communicated between protons and electrons, all these communicated things. Anytime there's communication between two bodies, there's something transferring between them that creates a pressure or a reason to move. That's a tension, and they can be under pressure. And anything that's under pressure has that tension, and that tension is what waves move through. It just really is a transfer of a change in one object that has a communication with another object, and when this one's affected, then this one's affected, and this one's affected, and this one's affected, and it's just a chain reaction of the change moving through the tension, through the force communication between objects. And those are what waves are. And the rest of the conversation about things, particles waving, doesn't really make any sense. There's no proof of any of those kinds of waves. Alright, all action is nuclear. Now, this isn't something they say, but I think most physicists would agree that when something happens, it happens on the subatomic level most. That's where it's really happening. That every little electron and every proton inside of this, when I move it, every single one of them has to be communicated with and told to move. It doesn't just move because something says move, says it in just that kind of way. Like there's just a notion that it should move. There has to be an actual physics, a physical connection between the electrons and the protons. They send a physical message to each other, essentially, a little push force that says move along, and that's how things move along. They don't move because nothing tells them to. They move like that wave analogy because there's a tension between everything. And if one thing moves, everything else feels it, and it decides to move too. But it's all that force, the communication between electrons and protons, that force, which they consider virtual photons, that is the cause of all action. The action is in the force. The matter doesn't do anything until the force tells it to. That's what the evidence indicates. Alright, there is a relationship between velocity and the rate of atomic decay. So this just gets to the time notion of a dimension. The real evidence is that we have real evidence that you can slow down atomic decay by speeding the atoms that are decaying, making them go faster. And the idea of what is going faster is the only part that's a little confusing, because acceleration sometimes doesn't mean you're acquiring velocity. You're just accelerating up and then accelerating down and accelerating up and accelerating down. That's not going to look like you're going somewhere, especially if you can't see the up and down. But it is in fact velocity. So acceleration is always has a component of velocity. So in a sense, acceleration, to be really correctly understood, would be understood as a subcategory of velocity. It's the acquisition of velocity, it can be, or it can just be a momentary velocity, where you accelerate in one direction and you accelerate in the opposite direction. But the point is you'll be moving in those directions, and you'll be moving at a rate, a timed rate. And that will decide your real velocity. So as I pointed out before, if somebody's bouncing a basketball, you could judge how far they're traveling across the court, or you could judge how much distance does the ball travel. So the ball's velocity is a lot higher than the person dribbling the basketball's velocity, because the ball is traveling a lot more distance. So you could argue that the notion of velocity is the controlling factor when you're in gravity. When you're in gravity, you really do have velocity. When you're standing on the earth and you appear not to be moving, you are in fact moving up and down. You're being bounced like a basketball, and at the same time you're being rotated across the surface of the Earth, and those combined motions add up to a substantial velocity. So you in fact have more velocity on the surface of the Earth than you would if you were floating above the Earth. And that's why satellites have their clocks need to be adjusted, is because technically the one in space is moving slower and is less dilated in terms of the fact that its radioactive decay takes place a little slower. But again, the only thing that's a real fact is that there is this relationship between velocity and decay. A time dimension isn't a fact, isn't a proven one. The fact that it can be warped or bent, none of that's proven. The evidence doesn't, there's no substantial evidence for any of those conclusions. Alright, light can be bent by traveling in close proximity to material substance. And realistically it comes down to electrons. Light encounters electrons, it will leave the encounter often in a new direction. So light doesn't hit electrons without the potential that the photon, the bit of light, will end up leaving in some new direction. And that's what you see in the two-slit experiment, and that's what you see with a single surface diffraction. But anytime the small aperture is really just about creating a surface that's got electrons around it, but it's a surface, and the surface interferes with the direction the light was traveling because it actually creates physical obstructions that change the direction of the light. Now there's real evidence for that relationship, that material objects will interfere with photons that go right next to their surfaces. Now all the other stuff they made up about Heisenberg and photons don't know where they are and they create waves and they do all this other stuff, that's all stuff sort of just made up. It's not stuff that there's hard evidence for. It's just their interpretation of this simple fact. The simple fact is light is disturbed by material objects. That's the real hard fact. The rest of it is just a bunch of speculation. And it should be judged compared to more, in my opinion, reasonable speculations. Alright, there is a relationship between the movement of electrons and the creation of magnetism, and vice versa, the movement of magnets and the creation of disturbance in electrons. And that's as far as the relationship really goes. And it seems, one can start arguing that what would that relationship be other than the same force that makes electrons repel each other, and the same force that makes protons and electrons attractive to each other. That this is obviously the same mechanism. So magnetism is essentially the force that makes electrons move, and it's just understanding how there's this difference between the force that moves a proton and the force that moves an electron. And I obviously have a simple explanation for that. But I'm just saying that's all we know is a fact, is that there's this relationship between the movement of these objects that are controlled by this force that's involved with moving electrons. Force does not interact with force, so as we could say, pretty strong. There's no real evidence that forces bounce off of each other. The evidence is that the force has to reach a material object before there's a bounce. So two things that have force can't have their forces interact and say let's just the forces bounce off each other. Things actually have to get close enough where the force from one reaches the material object of the other, and the forces interact with the matter. The forces don't add up and interact with each other, and that can be established through a lot of different proofs. The one exception that's known is the idea that somehow this gravity bends light. Now, that's again just based on really thin evidence, very incomplete documentation of the evidence, so arguably it's not an established fact that light is the exception, because in every other circumstance light isn't an exception. It's not bent by magnetism, and it's not bent by light. Light doesn't bend light. Clearly the force doesn't interact with the force. The speed of things moving, I think, can affect the frequency of effects they produce. So that would be red and blue shift. So the simple example is with sound. You can sort of understand kind of clearly that sound waves are being thrown, and the sound is a perturbation, a disturbance, a wave disturbance. So it's a lump, you could say, and then no lump, and then a lump, and no lump is kind of what sound is doing. And you can sort of understand that in the forward motion, the lumping, the thing producing the lump, is going to end up producing them closer together, because the movement's going to eat up the time it took to dump another bucket full. So if you had to dump a bucket of water off the front end of a car, the time it takes you to get a new bucket is sort of used up by the motion forward, and it will increase the tightness of the dumping, where the reverse would take place at the back, where if you're moving away, the distance problem is complicated, because now you're not using up the distance, you're adding more distance. So not only is there the distance of your movement, there's the time used up while you get another bucket of water, and that's more distance. And so now the buckets of water will end up being much further apart. And that basic idea is also true for light. That light's produced in the same way, in a sense that it's produced as bucketfuls of photon, and that the movement of the object that's producing the photon would have the same kind of problem if it's moving in the direction the whole object is moving. Now that's the catch with photons. They're produced by the little bits, and like with the example of the Earth, lots of the bits are moving in different directions at any one time. So the bit producing a photon could be going backwards, not forwards. Could be going twice as fast or twice as slow. Could be doing a lot of different things depending on what movement or motion the bits inside on the surface that's creating the light are moving. So you can't use it as a rule that this is always some kind of hard and fast rule that if an object's moving, it'll produce light that's going to be blue shifted, because it could be that the bits on the surface are not moving the same as the whole is moving. The bits producing the light might be moving a different direction, but the principle is still valid, that if the little electron is moving, then when it produces its photon, it's going to produce the wavelength. As it's producing the wavelength and it's moving, the wavelength's going to be getting shorter. If it's moving away, the wavelength's going to get longer. So it's a simple principle. Alright, there is background radiation, so that's about all you can say, right? There is background radiation. Now, do any of us know anyway? Maybe this is something to be researched, but how exactly intense is it? I mean, if you took all the photon energy from the universe, from the night sky, and you said how much photon energy is there? Is the microwave portion that much louder than the photon portion? And if it is, wouldn't that be expected? Because you'd sort of expect that the sun probably produces a lot of microwaves, that most of the heated objects in the universe are probably expelling some microwaves. Because in some sense, microwaves can be considered a form of infrared radiation. I mean, because we create this little light scale, it's because of what our eye can see. It doesn't mean that those frequencies are special. It just means that obviously those are the ones being produced by the sun in the most abundance, and they're the ones that have a really small wavelength, which means they're really good for seeing things. And if we saw all the other radiation, especially the infrared, that would just be noise, because it's bandwidth, it would create less detail. So it would make everything blurrier, because that extra information would be less information, not more information. So it would dirty our vision. Where if we could see in the ultraviolet, it would sharpen our vision. But the trick is the ultraviolet is damaging the cell, so obviously we didn't evolve to see in the ultraviolet spectrum, because it's difficult to make an eye that can do that without being destroyed by the radiation. But clearly it's just because of the circumstance that we evolved to maximize the spectrum. So clearly our body could see any parts of the spectrum, and it chose the parts that are the safest for the cells and have the maximum amount of information, in that the sun produces a lot of visible light, and it's it's a lot of radiation. But again, I don't have the numbers for exactly how much of this background, what's the intensity of this background radiation in all of these different frequencies, how much of it's in the FM band and the AM band, how much of it is a gigahertz or two, and how much of it's 10 gigahertz, 20 gigahertz, moving up towards the infrared range. We don't have that information. And what's the typical sun produce? These are all kind of like important details, because maybe the background radiation really isn't background radiation. It's just the overall radiation of everything radiating in the universe. Could be. I'm not sure on that. But anyway, the point is we know there is radiation. And the point is we didn't see it easily. So radiation can come in forms that we don't see, which is an important something to be conscious of, in the sense that there could be a lot of force, a lot of radiation, that we don't see it, therefore we don't think it exists. And that's sort of a mistake. So that's what I have so far. It's just a list of yes, these are facts. Now there's probably some other subtle ones, like let's see, you might be able to say that there's the periodic table, there's a certain number of elements, arrangements of atoms, so that might be a fact. That there's an association between the number of elements and weight. How much gravity affects something is sort of related to this idea of how many protons, or more precisely perhaps how many neutrons are in its atom. But these are going to start to get harder to define as what we know to be true versus the added stuff we throw in terms of assuming that assuming that electrons are affected by gravity, for example. Do we have any hard evidence that they are? I don't know. I haven't seen it myself, but that doesn't mean it doesn't exist. So anyway, yeah, any additions I'd appreciate, but I don't know. People aren't very interactive here, so I don't know if that's going to be of any use. But anyway, and so I'll just, I'm taking that start and saying, okay, now what do you do with that information? And I think you can start to draw some conclusions about the reality. So one of them would be that there's two kinds of force bit and two kinds of matter bit. In the sense that you kind of know that the electron is repelled by electrons because there's some sort of force that does that, and then there's some sort of force that repels protons from protons. So you have two different kinds of force, and clearly those interactions are just reversed when it comes to electron on proton or proton on electron. And so you could argue that yes, I can identify two kinds of force that exist. And I could argue that there's two kinds of a matter bit, in the sense that there's two kinds of matter relevant, and that is the electron, the negative charge, and the positive charge. And so we're just really talking about charges. And regular physics has added a whole bunch of other elements that they claim have all kinds of half charges and this, that, and the other thing. But those are the basic bits, and I would argue that the neutron is just a proton and an electron, which makes it a neutral bit, but it's clearly got components of both. So just two kinds of force bit, two kinds of matter bit, and you can start with that premise and, in my opinion, build the, create the entire checkerboard that is the universe out of the complex relationships you can end up getting by arranging those charges in patterns. So it's just the arrangement of charges in patterns, and that creates all the complexity that exists. Alright, so there's lots of little talking points. I might as well read down some of these things just since they're here and I'm here. So as I've sort of been mentioning last couple of videos, I think it's another one of these talking memes or points to be made, is that things that are like, when they called it the wave equation, Schrodinger's wave equation, it's really not a wave equation. It's just a pattern equation. It doesn't identify the source of the angular change. It just identifies the fact that there is an angular change, and you can rule in a lot of other causes for that angular change. They don't have to have anything to do with waves. So this is another where semantics is important. So just as the speed of force should be the terminology should be that it's a pattern equation, because it isn't fundamentally dependent on any notion of the existence of anything called a wave. It's the only thing that's relevant is the fact that there is something causing an angular change in direction. Alright, a wave of energy passing through connected tension. So I've sort of made that point that that's what a wave is. A wave is energy or change. I thought I changed that. Maybe I copied it and pasted that. Yeah. Passing through connected tension. It bothers me because I hope I didn't copy over an updated document, but whatever. So yes, it's just change, and when you change one item because of the tension, you'll change all of them because they're tied together like springs, and you can't affect one without affecting the others. Force bits have no connected tension, so that's an important thing. That force bits, the things like photons, things like the thing that makes magnetism, or the things that move electrons, those bits don't have any tension with each other. They don't repel each other. Photons of light don't repel each other. They don't attract each other. They have no connection to each other. They're not communicating with each other in any way. They can't tell each other to move left or tell each other to move right with some force, because they are force. And so there's just no tension in the forces. The forces cause tension between the matter bits. Alright, a wave of photons is as wrong as a wave of bullets. So I've said that before, but it's worth repeating. There's just no logical sense to creating something that you know is a corpuscle, and you know in every circumstance it just goes in a straight line, except when you put it right next to some kind of matter. Then all of a sudden it's not a straight line, but everywhere else it's a straight line unless it hits something. And there's just no reason to say that's doing this and this. So you have like a little lump of marble, and you're thinking this marble is doing this and doing this because it somehow has a magnetic reality and an electric reality, when there's no evidence that it's moved by either magnetism or electricity. No evidence at all. And yet this is their theory. Their assumptions, their interpretation of the evidence, and the evidence isn't there. Alright, where was I? Yeah, a wave of photons, I always said electrons and protons can't hold velocity. They can only be explicitly accelerated for an explicit moment. So this may or may not be true. I'm just not sure. I mean, this isn't in the list of facts. This is my theory stuff. But it's not even my theory. I'm just saying I think these are close to being true statements about these objects. That you can't throw an electron into outer space and make it go to Mars. It'll stop. and a proton will do the same thing. They just won't keep going. They don't hold a velocity because they are actually going through a dense force field, and the force field will, the charge field, some people would call it a charge field, will consume their velocity. Forces don't interact with forces. That forces affect matter, matter affects force. So obviously the communication between force and force happens with the matter bit. It's the communicator, the conduit. So if a force pushes on this side, this force will know about it if a piece of matter tells it about it. But it has to be communicated through the matter, and matter can only communicate with matter by doing the same thing. You know, they're not allowed to invert their roles. Probably have to call that. So anyway, force affects matter, matter affects force. Okay, all velocity originates with the velocity of force. So that's a big one in this whole story, is the speed of force is the speed really of everything, because everything is all the communication. The forces all move the speed of light. When they communicate to a piece of matter, they communicate with a little burst at the speed of light, and then that speed has to be spread over them. So when one photon hits me, it gives me momentum at the speed of light in a direction, but that speed has to be spread over the gazillions and gazillions of other little bits of material crap inside of me. Every single one of those little bits in some way has to go with the flow, so to speak. So the flow is turned into, so something that's the speed of light is turned into the speed of a prehistoric snail or something. I mean, it's turned into an incredibly slow velocity. But that's, get hit by enough of them, then you'll have a real velocity. But it takes a lot of them. But that's really the source of the movement. The force has the movement. The matter is just a victim of changes in the force pressure, changes in the balance of pressure. Okay, force affects matter. Okay, all velocity, yes. Force is pressure. Well, I just said it, so yeah. Alright, so I don't think we'll get into the specifics of gravity and some of this other stuff. And I have the whole thing on drag here and all the rest of those arguments to be made in the future, and the two slit and whatever, and I'm just trying to narrow the conversation and point out that there's a logical way to understand how most of modern physics is not made out of stuff that we have hard evidence for. That they're kind of, I won't say, I could say reckless assumptions, but they're kind of desperate assumptions. They want an answer, and so they're jumping before it's ready. They're hungry and they want to eat it now, and they just really don't want to wait until it's cooked. And that happened 100 years ago, and physics is just, it's built a really ugly monstrosity of a house, a standard model, on just a lot of wrong notions of how you basically do this, piling bricks on top of each other. They've built a monstrosity, they haven't built on a solid foundation. It's not a pyramid. It's a lot messier. Alright, so that's probably enough of a video. And yeah, I gotta, I'm really my brain just doesn't want to do this writing thing, and I know I gotta do it, but I just don't want to do it. So anyway, I gotta work on that. Brain's nagging me, but it just isn't working yet, so I've got to come up with a strategy. Anyway, till the next time. And I mean, it's simple, but it's complicated, I mean, it's complicated unraveling all the things people expect physics to be. And so you have to make them understand why those expectations of dimensions and multiverses and magical properties just isn't necessary. So anyway, enough. Till the next time, and such.